Right now, as you're watching this, you're hurtling through the cosmos at over 500,000 miles per hour. Not in a spaceship, not through some science fiction technology, just sitting there wherever you are, carried along by forces so vast and so powerful that our entire existence unfolds within their grip without us feeling even the slightest tremor. You're being dragged through space by a star that's racing around something monstrous, something with gravity so intense it holds 400 billion stars in its thrall. At the heart of our galaxy, the Milky Way, sits a supermassive black hole 4.3 million times more massive than our Sun. It's called Sagittarius A star, and it's the anchor point around which our entire cosmic neighborhood revolves. Tonight, we're taking you on a journey from Earth, from your chair, from this moment in time, all the way to that monster's edge. We'll travel through stellar graveyards where dead stars drift in the darkness. We'll pass through gas clouds so vast they dwarf our entire solar system. We'll witness stars being born in cosmic nurseries and others being torn apart by gravitational forces that warp the very fabric of space and time. This isn't just another trip through the stars. This is a journey that will change how you see your place in the universe. If you're ready to discover what our galaxy really looks like from the inside out, stick around, because we're about to dive deep into one of the most spectacular structures in the known universe. Our starting point, Earth's incredible cosmic motion. We begin here on Earth, but let's be clear about something right from the start. This planet is not sitting still. Nothing in the universe is sitting still. Right now, at this very moment, our entire solar system is plowing through space at 67,000 miles per hour. That's faster than any rocket humans have ever built. It's faster than anything we've sent to other planets. Faster than the Voyager spacecraft that left our solar system decades ago. You might think we're just orbiting peacefully around the sun, following a nice gentle ellipse through space. And yes, Earth does orbit the sun, but that's only a tiny part of the story. The sun itself is dragging us along on a much wilder ride. Picture our solar system like a speedboat racing across an ocean. The sun is the boat, and all the planets, all the moons, all the asteroids and comets, we're all passengers getting pulled along for the journey. We're not just floating randomly through space either. We're following a specific path around the center of our galaxy, completing one full lap every 225 to 230 million years. Think about that for a second. The last time Earth was in this exact spot in the galaxy, dinosaurs didn't even exist yet. The continents were arranged differently. Life on Earth was still mostly confined to the oceans. One orbit ago, and our entire world was unrecognizable. But here's where it gets even stranger. As we race around the galaxy, we're also bobbing up and down like that speedboat hitting waves. Every 33 million years or so, our solar system passes through the flat disk of the Milky Way, then rises above it, then dips below it. Some scientists think these crossings might trigger mass extinctions on Earth. When we pass through the galactic disk, we encounter more cosmic radiation, denser asteroid fields, and gravitational chaos from passing stars and gas clouds. Think of it like driving through different neighborhoods in a massive city. Sometimes we're in quiet suburbs with nothing but empty space around us. The cosmic equivalent of tree-lined streets and peaceful parks. Other times we're speeding through busy downtown areas packed with stars, gas clouds, and cosmic debris. Right now we're in one of the quieter neighborhoods, and that might be why life had a chance to develop on our planet in the first place. The strangest part is that we're not traveling alone through this emptiness. Our solar system sits inside a huge bubble of hot, thin gas that stretches for over 1,000 light-years in every direction. This bubble was carved out by massive stars that exploded millions of years ago. Their explosion swept away most of the dense gas and dust, leaving us in this relatively empty pocket of space. Without this protective bubble, Earth might look very different today. Dense clouds of gas and intense cosmic radiation could have made it much harder for life to survive and evolve. We're essentially living inside the aftermath of ancient stellar violence. We're cruising through a cavern hollowed out by star death, protected by the very forces that could have destroyed everything. When you look up at the night sky, you're seeing the edge of this bubble in every direction. Those distant stars you can make out with your naked eye. They're mostly on the far side of our cosmic neighborhood, shining through the thin walls of our protective shell. We're like passengers in a glass submarine, traveling through the deep ocean of space, and our journey to the galactic center starts here, in this quiet bubble of space. But as we venture outward from our solar system, as we begin to accelerate our journey toward the heart of the Milky Way, we're going to discover that our peaceful neighborhood is surrounded by forces and structures that absolutely dwarf anything we can see from Earth. The local bubble, born from stellar violence. The bubble of space around us has a name among astronomers. They call it the local bubble, and it's one of the most fascinating structures in our immediate cosmic vicinity. This cosmic cavern stretches over 1,000 light-years across. To put that in perspective, if you could travel at the speed of light, it would take you more than 1,000 years to cross from one side to the other. And we're drifting through it like a speck of dust floating through a cathedral. But this cathedral wasn't built. It was carved by violence. About 10 to 20 million years ago, give or take a few million years, a group of massive stars lived and died in this region of space. When stars over 8 times heavier than our Sun reach the end of their lives, they don't fade away quietly, like our Sun will someday. They don't just cool down and become white dwarfs. They explode. They explode as supernovas, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. These explosions didn't happen just once. They happened over and over again as star after star in this region reached its violent end. Each supernova blast swept outward like an invisible tsunami, pushing gas and dust away from the explosion site at incredible speeds. When multiple supernovas go off in the same region over millions of years, they create what astronomers call a superbubble. Our local bubble is one of these cosmic hollows, and it's still expanding outward from those ancient explosions even today. Imagine throwing stones into a calm pond. Each stone creates ripples that spread outward in circles, pushing water ahead of them. Now, imagine throwing dozens of stones into the same area over and over again for hours. The overlapping ripples would create a complex pattern of waves and calm spots, interference patterns that change the entire surface of the water. That's what happened here in our region of the galaxy. Except instead of stones and water, we're talking about stellar explosions and the fabric of space itself. The walls of our bubble aren't empty. They're made of hot gas that's been heated to over 1 million degrees by those ancient explosions. This gas is incredibly thin. A cubic inch of it contains fewer atoms than the best laboratory vacuum on Earth. Yet it blows with X-ray light, invisible to our eyes but detectable by space telescopes orbiting above our atmosphere. We're not at the center of this bubble either. Our solar system is actually closer to one edge, drifting toward a region where the bubble wall is starting to thicken with cooler gas and dust. In about 5 million years, we'll punch through this wall and enter a much denser part of the galaxy. When that happens, our solar system will face new challenges. The thin bubble of hot gas around us acts like a shield, deflecting some of the cosmic radiation that would otherwise bombard Earth. When we leave this protection and enter denser regions of space, our planet's atmosphere will encounter more high-energy particles from deep space. Some scientists wonder if this could trigger climate changes or even mass extinctions. There's some evidence that past crossings through dense interstellar clouds might correlate with extinction events in Earth's geological record. It's not certain, but it's one of those connections that makes you realize just how connected we are to the larger cosmic environment. For now, though, we're sailing through this cosmic safe harbor, protected by the aftermath of stellar death. The irony is perfect. The same explosions that could have sterilized any planets in this region millions of years ago now provide a buffer zone that helped life flourish on Earth. We exist in the protective shadow of ancient destruction. Star birth in our cosmic neighborhood. But our peaceful journey through the local bubble is about to encounter something extraordinary. Just 13,300 light-years from Earth, something magnificent is happening in the darkness. Giant clouds of gas and dust are collapsing under their own gravity, and deep inside these cosmic cocoons, new stars are igniting for the first time. The nearest major star-forming region to us is so active, so energetic, that if our eyes could see infrared light, it would glow brighter than almost any other star in our night sky. This stellar nursery is part of the Orion molecular cloud complex, and it's a factory for making suns. Picture a cloud of gas and dust so vast that light takes several years to cross from one side to the other. These clouds contain thousands of times the mass of our Sun, all of it cold and dark, drifting through space. Now imagine that cloud slowly contracting like a giant hand squeezing a sponge. As the cloud shrinks, it fragments into smaller pieces, and those pieces continue to collapse under their own weight. As each fragment shrinks, it heats up. The atoms inside are being pulled closer together, colliding more frequently, moving faster. The center of each collapsing fragment gets hotter and hotter, denser and denser, until finally, after millions of years of slow contraction, something incredible happens. The temperature at the center reaches 10 million degrees, and nuclear fusion begins. Hydrogen atoms start fusing together to form helium, releasing enormous amounts of energy. A new star lights up for the first time. But starbirth is not a gentle process. When a new star switches on, it blasts out winds of particles at speeds of hundreds of miles per second. These stellar winds carve bubbles and caverns in the surrounding gas cloud, creating structures that look like cosmic sculptures. Some of these newborn stars are so massive and so energetic that they illuminate entire sections of their birth cloud, creating glowing nebulae visible from thousands of light-years away. The process takes millions of years, which sounds like an incredibly long time, until you realize that most stars will shine for billions of years. It's like watching a flower bloom, except the flower is bigger than our entire solar system, and it will burn brighter than 1 million suns for eons to come. Not every clump of gas becomes a star, though. Some collapse partway and become brown dwarfs, failed stars that never got quite hot enough to ignite nuclear fusion. They glow dimly in infrared light, radiating away the heat from their formation. But they'll never shine like true stars. Others get torn apart by the winds and radiation from their more successful neighbors before they ever have a chance to ignite. What makes this even more remarkable is that stars are not born alone. When a gas cloud collapses, it usually fragments into dozens or hundreds of pieces, each becoming its own star. These stellar siblings start life clustered together in tight groups, sharing the same cosmic neighborhood. They're all roughly the same age, all born from the same cloud of gas, all made from the same cosmic ingredients. Over millions of years, though, they gradually drift apart. Gravity from the rest of the galaxy pulls them in different directions. Close encounters with other stars give some of them kicks of velocity that send them wandering away from their birth cluster. Eventually, most clusters dissolve completely, and the stars scatter across the galaxy, their common origin forgotten. Our own sun was born this way, about 4.5 billion years ago, in a cluster with thousands of other stars. Those stellar siblings are now scattered across the galaxy, impossible to identify because they've traveled so far from their birthplace. Somewhere out there among the hundreds of billions of stars in the Milky Way are the long-lost brothers and sisters of our Sun. Stars that formed in the same nebula, from the same cloud, at the same moment in cosmic history. The Orion Arm, our galactic highway. The star formation happening in nearby regions gives us a window into our own origins. But these stellar nurseries are just the beginning of our galactic journey. As we venture farther from Earth, as we start to see the larger structure of our galaxy, we encounter something that early astronomers had no idea even existed. A massive structure that we're embedded in, that we've been traveling through for our entire existence. The Orion Arm, also called the Local Arm, is a minor spiral arm of the Milky Way that stretches for thousands of light years in both directions from our position. We're not just riding along with this structure. We're actually woven into its fabric, part of its very substance. Think of the Milky Way galaxy like a massive hurricane seen from space. The bright spiral arms you see in pictures of other galaxies. They're like the storm's bands of clouds, except instead of water vapor, these arms contain stars, gas, and dust. Most spiral galaxies have 2 or 4 major spiral arms, but they also have smaller arms and spurs branching off from the main structure, like tributaries feeding into rivers. For decades, astronomers thought we lived in a tiny spur, barely worth mentioning, connecting 2 major arms. Just a minor feature, a cosmic side street. But recent observations have revealed something surprising. The Orion Arm is much larger and more substantial than anyone realized. It extends for over 20,000 light years, making it a significant galactic feature in its own right. We're not living in a cosmic backwater after all. We're part of a major galactic structure. This spiral arm contains some of the most famous objects in our night sky. The bright stars of Orion, Perseus, and Cygnus all belong to our local arm. So do many of the stellar nurseries where new stars are being born, including those vast molecular clouds we just explored. The arm acts like a gravitational river, channeling gas and dust into dense streams where star formation can occur. But spiral arms aren't permanent structures carved into the galaxy. They're more like traffic jams on a cosmic highway. As material orbits the galaxy, it gets bunched up in certain areas, creating the appearance of spiral patterns. Stars and gas clouds flow into the arms, spend some time there compressed and interacting, then flow back out into the spaces between arms. Our solar system has probably drifted in and out of spiral arms multiple times during its 4.5 billion-year journey around the galaxy. Each time we enter an arm, the density of stars and gas around us increases. The gravitational forces become more complex. The radiation environment becomes more intense. Each time we exit an arm, things quiet down again. The density difference between arms and the spaces between them affects star formation rates across the galaxy. When gas clouds enter a spiral arm, they get compressed by the increased gravitational forces and higher densities. This compression can trigger the collapse of gas clouds into new stars, like squeezing a sponge releases water. Then, as massive stars form and eventually explode as supernovas, they can disrupt nearby star formation by heating and dispersing the gas, or trigger even more stellar bursts by compressing neighboring clouds. We're currently positioned about halfway between the galaxy's center and its outer edge, in what astronomers call the Galactic habitable zone. This might not be a coincidence. Closer to the center, there's too much radiation and too much gravitational chaos for stable planetary systems to survive long enough for life to evolve. The density of stars is so high that close encounters with other stars could disrupt planetary orbits. Supernova explosions happen more frequently, bathing everything in deadly radiation. Farther out toward the galaxy's edge, though, there's a different problem. There aren't enough heavy elements to build rocky planets like Earth. Stars in the outer galaxy formed from more primordial gas that hadn't been enriched by as many generations of stellar life and death. Without those heavy elements, without carbon and oxygen and silicon and iron, you can't build the complex chemistry needed for life as we know it. Our location in the Orion arm puts us in a cosmic sweet spot, far enough from the center to avoid the chaos, close enough to benefit from the chemical enrichment of billions of years of stellar evolution. It's one of those details that makes you wonder about the universe and our place in it. The incredible speed of our galactic orbit. Let's talk about speed for a moment. Real speed, cosmic speed. The kind of speed that changes how you think about motion forever. You're not just sitting there reading this. You're racing through space faster than a rifle bullet, faster than a jet fighter, faster than anything humans have ever built. And that's just the beginning of your cosmic velocity. Right now, Earth is spinning on its axis at over 1,000 miles per hour at the equator. That's your first layer of motion, the one you probably learned about in school. But Earth is also orbiting the Sun at 67,000 miles per hour, carrying you along for the ride. Most people know about these motions, at least in an abstract way. But they're nothing, absolutely nothing, compared to what comes next. Our entire solar system is orbiting the center of the Milky Way galaxy at somewhere between 450,000 and 560,000 miles per hour, depending on whose measurements you trust. Let's use a conservative estimate and say 500,000 miles per hour. Let that sink in for a moment. Every second, you travel about 140 miles through space just from galactic rotation. If you could somehow step outside this motion and watch our solar system pass by, we would streak past you faster than your eye could track. But even that's not the full story. Our galaxy itself is moving through space. The Milky Way is falling toward a massive galaxy cluster called the Virgo cluster at over 1 million miles per hour. And the Virgo cluster itself is being pulled toward an even larger structure called the Great Attractor, a gravitational anomaly so massive it's influencing the motion of galaxies across hundreds of millions of light years. When you add up all these motions, Earth's rotation. Earth's orbit around the Sun. The Sun's orbit around the galaxy. The galaxy's motion through space. You're traveling through the universe at roughly 1.3 million miles per hour. Think about that. In the time it took you to watch the first few minutes of this video, you've traveled thousands of miles through space, tens of thousands, and you never felt a thing. There's no cosmic wind in your hair, no sense of acceleration pushing you back in your seat. You're surfing through the universe at mind-bending speeds, and the only reason you don't feel it is because everything around you is moving together. Your chair, your house, the air you breathe, the ground beneath your feet, all of it is being carried along by the same gravitational currents. This galactic motion has real consequences beyond just impressive numbers. As our solar system orbits the galaxy, we encounter different environments. Sometimes we pass through the galaxy's spiral arms where star formation is active and radiation levels are higher. Other times we cruise through quieter regions between the arms, like we're doing now. Our orbital speed also means we complete one full trip around the galaxy every 225 to 230 million years. Astronomers call this period a galactic year. Since Earth formed about 4.6 billion years ago, we've completed roughly 20 galactic years. Just 20 complete orbits. The last time we were at this exact position in our galactic orbit, the most complex life on Earth was simple. Marine creatures. Dinosaurs, mammals, flowers, birds, and humans have all evolved during our current trip around the galaxy. The Milky Way's rotation isn't uniform either. Stars closer to the center orbit faster, while stars at the outer edges move more slowly. This is called differential rotation, and it's what maintains the galaxy's spiral structure. If everything rotated at the same speed like a solid disk, the spiral arms would wind up too tightly and disappear within just a few 100 million years. The galaxy would lose its beautiful spiral structure and become a featureless disk. Stellar graveyards and cosmic corpses. As we journey deeper toward the galactic center, passing through our local neighborhood and beginning to see the larger structures of the galaxy, we need to talk about what lies hidden between the bright stars. Between the lights that illuminate our night sky lurk the cosmic dead. Scattered throughout our local region of the galaxy are the remnants of stars that burned out long ago, leaving behind objects so strange they seem like something out of science fiction. These stellar corpses are invisible to our eyes, but they're everywhere around us. And some of them are among the most dangerous objects in the universe. The most common residents of stellar graveyards are white dwarf stars. These are the dense, hot cores left behind when stars like our Sun reach the end of their lives. After our Sun exhausts its nuclear fuel in about 5 billion years, it will swell up into a red giant, shedding its outer layers into space. What remains will be a white dwarf, a sphere roughly the size of Earth containing about 60% of the Sun's mass. Let that sink in. An object the size of our planet, containing more mass than the Sun. A white dwarf is so dense that a teaspoon of its material would weigh as much as a car. The nearest white dwarf to us is only 8.6 light-years away, making it one of our closest stellar neighbors. We just can't see it without powerful telescopes because it's so dim. White dwarfs start incredibly hot, over 100,000 degrees on their surface, but they have no internal source of energy anymore. No fusion reactions keeping them hot. They slowly cool down over billions of years, radiating their heat into space like a dying ember. Some of the oldest white dwarfs in our galaxy have been cooling for so long that they're now colder than our sun's surface. These ancient stellar corpses are like cosmic time capsules, preserving information about stars that died when the universe was young. But white dwarfs can come back to life in spectacular fashion. If a white dwarf has a companion star in a binary system, it can steal material from its partner through gravitational theft. The intense gravity of the white dwarf pulls gas off the companion star, and this material spirals down onto the white dwarf's surface. When enough stolen material builds up, it triggers a thermonuclear explosion called a nova. The explosion blows away the accumulated material in a brilliant flash, and the process can repeat itself over and over again, sometimes for millions of years. Even stranger are the neutron stars hiding in our galactic neighborhood. When a star at least 8 times more massive than our Sun explodes as a supernova, its core can collapse into something almost beyond imagination. The atoms themselves are crushed. Electrons are forced into protons, creating neutrons. What's left is a neutron star, a sphere only about 12 miles across, but containing more mass than our Sun. A neutron star is so dense that a sugar cube-sized piece would weigh 6 billion tons. That's more than Mount Everest compressed into something you could hold in your hand, if your hand could somehow withstand the gravitational forces. The entire star, containing more mass than our Sun, gets crushed into a sphere about the size of Manhattan. Some neutron stars spin hundreds of times per second while blasting beams of radiation from their magnetic poles. If those beams sweep across Earth like lighthouse beams sweeping across the ocean, we detect them as regular pulses of radio waves. These objects, called pulsars, are like cosmic lighthouses with timing so precise they rival atomic clocks. The fastest spinning pulsar known rotates 716 times every single second. Imagine something more massive than our Sun, spinning around 700 times per second, and you start to get a sense of the extreme physics at work here. The surface of that pulsar is moving at a significant fraction of the speed of light. The magnetic fields around neutron stars are trillions of times stronger than Earth's magnetic field. If a neutron star were placed where our moon is, its magnetic field would be so intense it would erase every credit card on Earth. Every computer hard drive, every piece of magnetic media. Getting within 600 miles of a neutron star would be instantly fatal, as the magnetic field would disrupt the electrical activity in your nervous system, stopping your heart and brain function. These stellar graveyards aren't just cosmic curiosities, they're laboratories for studying physics under conditions impossible to create on Earth. They help us understand what happens to matter under extreme gravity, temperature, and magnetic fields. They test our theories of physics in ways we could never achieve in any laboratory. Into the major spiral arms. As we leave our local spiral arm behind and venture deeper into the galaxy, accelerating our journey toward the center, we encounter something that dwarfs our cosmic neighborhood. The Perseus arm is one of the Milky Way's major spiral arms, a galactic superhighway packed with more stars, more gas, more cosmic activity than anything we've seen so far. It's like stepping from a quiet suburban street onto a busy interstate, from a small town into a major city. This massive structure contains some of the most luminous and energetic stars in our galaxy. While our local arm is home to relatively modest stars and star-forming regions, the Perseus arm hosts stellar monsters. Stars here can be 50 or even 100 times more massive than our Sun, burning so bright and hot that they appear blue-white to our telescopes. These giants live fast and die young. typically burning out in just a few million years instead of the billions of years that smaller stars enjoy. The Perseus arm gets its name from the constellation Perseus, which lies in the same direction when viewed from Earth. But this spiral arm extends far beyond what we can see with the naked eye. It stretches for tens of thousands of light years, wrapping partway around the galaxy like a loosely coiled spring. If you could shrink the Milky Way down to the size of a dinner plate, the Perseus arm would be one of the major curves you'd see spiraling outward from the center. What makes spiral arms like Perseus so active? They're regions where the galaxy's density wave patterns pile up gas and dust, creating perfect conditions for massive star formation. Think of it like a traffic jam on a highway. Cars bunch up in certain areas, move slowly through the congestion, then spread out again on the other side. Gas clouds do the same thing as they orbit the galaxy, getting compressed when they enter spiral arms and triggering bursts of star formation. The Perseus arm contains some of the most spectacular stellar nurseries known to astronomy. One of them, called the Eagle Nebula, is famous for the pillars of creation. Towering columns of gas and dust where new stars are being born. These pillars stretch for several light years and are being carved by the intense radiation from nearby massive stars, like wind and rain sculpting rock formations over millions of years. Another region, the Rosette Nebula, glows bright red from ionized hydrogen gas heated by a cluster of hot young stars at its center. The nebula looks like a cosmic flower, petals of glowing gas surrounding the brilliant stars that illuminate it. But the Perseus arm isn't just about starbirth. It's also home to some of the most violent stellar deaths. When those massive blue stars reach the end of their brief lives, they explode as supernovas with the energy of billions of suns. These explosions can be seen from other galaxies, millions of light years away, briefly outshining entire galactic arms. They also inject heavy elements into space, enriching the surrounding gas with carbon, oxygen, silicon, iron, and all the other building blocks needed for rocky planets and potentially life itself. Traveling through the Perseus arm would be like driving through a cosmic construction zone. Everywhere you look, there's activity. Stars being born in glowing nebulae, stars exploding and scattering their guts across space, gas clouds colliding and merging, their contents mixing and swirling, intense radiation fields that would sterilize any unprotected spacecraft. It's beautiful and deadly at the same time, creation and destruction dancing together on cosmic scales. Even larger than the Perseus arm is the Scutum Centaurus arm, the longest and most massive spiral arm in the Milky Way. This is a cosmic structure so vast it wraps more than halfway around the entire galaxy. If the Perseus arm was a busy highway, this is a superhighway carrying the bulk of our galaxy's star formation and stellar activity. The Scutum Centaurus arm extends for over 60,000 light-years, making it longer than the distance from Earth to the galactic center and back again. It contains some of the most active star-forming regions in the entire galaxy, places where new stars are being born at rates thousands of times higher than in our quiet local neighborhood. What makes this arm so special is its proximity to the galactic center. As one of the inner spiral arms, it receives a constant flow of gas and dust from the galaxy's central regions. This material gets funneled along the arm's length, creating an almost continuous chain of stellar nurseries and massive star clusters. The arm acts like a cosmic assembly line for manufacturing stars. The star formation rate in the Scutum Centaurus arm is staggering. In some regions, new stars are being born at a pace that would, if sustained, convert gas into stars faster than the galaxy can replenish it. These aren't just ordinary stars either. The arm specializes in producing stellar monsters, stars with masses 50 to 100 times greater than our Sun. When these giants explode as supernovas, they can briefly outshine entire galaxies. The galactic bar, hidden architecture. Hidden at the heart of our galaxy lies a secret that astronomers only discovered in recent decades. The Milky Way isn't just a simple spiral galaxy with arms emerging from a circular center. At its core stretches a massive bar-shaped structure made of stars and gas, invisible from Earth in optical light, but revealed by infrared observations. This galactic bar is larger than anything we've encountered so far, and it's the hidden backbone that controls the flow of matter throughout our entire galaxy. Picture the Milky Way from above, and instead of seeing neat spiral arms emerging from a circular center, you'd see something that looks more like a cosmic barbell. The galactic bar stretches for over 27,000 light-years from end to end, making it roughly half the diameter of the entire galactic disk. This massive structure rotates as a single unit, spinning faster than the surrounding spiral arms. The bar formed billions of years ago through a process called bar instability. As the galaxy aged and stars settled into more circular orbits, gravitational interactions between stars began creating elongated patterns. Over hundreds of millions of years, these patterns grew stronger and more organized until they formed the rigid bar structure we see today. About 2/3 of all spiral galaxies have similar bars at their centers, so we're not unique in this respect. But this isn't just a static structure sitting at the galaxy's center. The galactic bar acts like a cosmic pump, channeling gas from the outer galaxy toward the center through a process called gravitational torquing. As gas clouds orbit the galaxy and encounter the bar's gravitational field, they get deflected from circular orbits into elongated paths that spiral inward. It's like water flowing down a drain, except the drain is 27,000 light-years long and made of billions of stars. This inward flow of gas has profound consequences for the entire galaxy. The bar has been feeding material to the galactic center for billions of years, building up the massive structures and dense stellar populations we find there. Without the bar's pumping action, the central regions of our galaxy would be much quieter, much less active places. The supermassive black hole at the very center might be smaller. The nuclear star cluster might not exist. The whole inner galaxy would look different. The bar also affects the motion of stars throughout the galaxy. Stars that venture too close to the bar can get gravitationally scattered onto new orbits, sometimes being flung toward the galactic center or ejected toward the outer regions. Our own solar system may have encountered the bar's influence during its 4.5 billion-year journey around the galaxy. Though we're currently in a safe region well outside the bar's direct effect, recent observations have revealed that the galactic bar isn't perfectly smooth. It contains its own spiral structure, with dense lanes of gas and dust wrapped around the bar's length like cosmic DNA strands. These bar spirals are some of the most active star-forming regions in the galaxy, powered by the constant inflow of fresh material from the outer regions. The bar's rotation rate is precisely tuned to maintain the galaxy's spiral structure. If it rotated too fast or too slow, the spiral arms would either wind up too tightly or unwind completely within a few 100 million years. This delicate balance has kept the Milky Way's basic structure stable for billions of years, allowing it to maintain its characteristic spiral appearance. The central molecular zone, gas giants near the core. as we follow the bar's gravitational channels toward the galactic center, as we accelerate our journey into the inner regions of our galaxy, we're approaching an environment unlike anywhere we've been before. Welcome to the most extreme neighborhood in the Milky Way, the central molecular zone. This is a ring of molecular clouds surrounding the galaxy's center, just a few hundred light-years from the supermassive black hole, and it's a place where the laws of physics are pushed to their absolute limits. This is where cosmic violence and stellar birth collide in ways that would be impossible anywhere else in the galaxy. The entire central molecular zone spans about 1,000 light-years across, but it contains as much gas and dust as the rest of the inner galaxy combined. That's enough raw material to build 10 million stars like our Sun, all packed into a region that represents less than 1% of the galactic disk's area. If our local region of space has the density of air, the central molecular zone has the density of water. Scattered through this region lurk molecular clouds so massive they dwarf entire solar systems. Cosmic titans containing enough raw material to build millions of stars. These aren't the modest stellar nurseries we found in our local neighborhood. These are the galaxy's heavy industry zones, where star formation happens on a scale that defies comprehension. The largest of these giants is called Sagittarius B2, a molecular cloud complex located just 390 light-years from the galactic center. This single cloud contains enough material to build 3 million stars like our Sun. If you could somehow compress our entire solar system down to the size of a marble, Sagittarius B2 would still be larger than a football stadium. The cloud is so massive that its gravitational pull affects the orbits of nearby stars. But size isn't the only thing that makes these clouds remarkable. The conditions inside them are unlike anything in our quiet corner of the galaxy. Temperatures drop to just 10 degrees above absolute zero, making them some of the coldest places in the universe. At these frigid temperatures, hydrogen atoms stick together to form hydrogen molecules, creating a dense fog of gas and dust particles. The chemistry happening inside these clouds reads like a cosmic cookbook. Over 200 different molecules have been detected in interstellar space, from simple water and carbon monoxide to complex organic compounds that could serve as building blocks for life. Some clouds contain vast quantities of ethyl alcohol. Sagittarius B2, in fact, contains enough alcohol to supply every person on Earth with 300,000 pints of beer per day for the next billion years. Other regions harbor molecules that smell like raspberries or taste like rum, complex organic compounds floating in the darkness of space. These molecular giants don't just sit passively in space either. They're constantly being stirred and heated by radiation from nearby stars, shockwaves from supernova explosions, and magnetic fields that thread through the galaxy. This turbulence creates complex internal structure with dense cores, expanding shells, and streaming flows of material. The clouds are like cosmic weather systems, complete with their own storms and circulation patterns. But here's the strange thing. Despite containing enough material to trigger explosive star formation, this region is surprisingly quiet. The star formation rate in the central molecular zone is actually 10 to 100 times lower than it should be based on the available gas supply. Something is preventing these massive molecular clouds from collapsing into stars, and astronomers are still trying to understand why. The answer lies in the extreme conditions near the galactic center. Intense magnetic fields, stronger than anywhere else in the galaxy by factors of thousands, thread through the molecular clouds like invisible steel cables. These fields are strong enough to support the clouds against gravitational collapse, preventing the normal cascade of star formation we see elsewhere in the galaxy. The magnetic field strengths here are thousands of times stronger than anything in our solar neighborhood. These fields accelerate particles to incredible speeds, creating streams of cosmic rays that race throughout the galaxy. Some of these high-energy particles eventually reach Earth, where they're detected by cosmic ray observatories as showers of subatomic particles raining down through our atmosphere. The temperatures in this region tell a story of cosmic violence. While the dense molecular cloud cores remain cold, just a few degrees above absolute zero, the spaces between clouds are filled with gas heated to millions of degrees by shock waves from stellar explosions and energy from the central black hole. This creates a bizarre environment where freezing cold molecular gas exists just light years away from plasma hot enough to strip electrons from atoms. When star formation does happen in the central molecular zone, it produces some of the most massive stars known to exist. These stellar monsters can be over 100 times more massive than our Sun, burning so hot and bright that they appear blue-white even from thousands of light-years away. They live fast and die young, typically exploding as supernovas within just a few million years of their birth. The nuclear star cluster, cosmic crowding. At the very heart of our galaxy, packed into a space smaller than the distance from Earth to our nearest stellar neighbor, live over 25 million stars. This is the nuclear star cluster, the densest collection of stars in the Milky Way and one of the most crowded places in the known universe. If our solar system existed here, the night sky would contain thousands of stars brighter than our full moon. The stellar density in this region defies imagination. While the nearest star to our Sun is 4.24 light-years away, that vast gulf of empty space, stars in the nuclear star cluster can be separated by distances smaller than our solar system. In the very center, stellar neighbors might be only a few billion miles apart, close enough that their outer atmospheres could interact during close approaches. Planetary systems would be impossible here. The gravitational chaos would tear apart any orbiting worlds within thousands or tens of thousands of years. A planet orbiting a star in the nuclear star cluster would constantly be tugged by the gravity of neighboring stars, its orbit perturbed and destabilized. Eventually, it would either be ejected from the system entirely or fall into its host star. But these aren't ordinary stars crowding together either. Many of the cluster's residents are stellar exotics, objects that form only under the most extreme conditions. Wolf-Rayet stars burn so hot they blast away their outer layers in stellar winds traveling thousands of miles per second, losing mass at prodigious rates. Red supergiants swell to sizes larger than Earth's orbit around the Sun, their surfaces extending past where Mars orbits in our solar system. Blue hypergiants shine with the luminosity of millions of suns, burning through their nuclear fuel so rapidly they'll explode within just a few million years. The gravitational environment here operates by different rules than anywhere else in the galaxy. Stars don't follow simple elliptical orbits like planets around the Sun. Instead, they trace complex rosette patterns as they're tugged by the combined gravity of millions of neighbors and the supermassive black hole at the center. Some stars follow such elongated orbits that they swing from the cluster's edge nearly to the black hole's event horizon and back again, experiencing wildly different gravitational forces at different points in their orbits. The cluster formed through a process that took billions of years. As gas flows spiraled inward toward the galactic center, they triggered bursts of star formation in the dense environment near the supermassive black hole. Over time, these stellar generations built up into the massive cluster we see today. But star formation here wasn't a gradual, steady process. It happened in violent episodes triggered by major gas infall events, creating distinct populations of stars with different ages and compositions. Life cycles here are compressed and accelerated. Massive stars form, live and die within just a few million years, their entire existence playing out on timescales that are almost instantaneous by cosmic standards. Their supernova explosions add to the chaos, injecting energy and heavy elements into the cluster's environment. The cluster contains dozens of stellar mass black holes, neutron stars, and white dwarfs, all packed into the same small volume with the living stars. When these compact objects encounter each other, they can spiral together and merge, creating gravitational wave signals that ripple across the universe. In fact, the dense environment of the nuclear star cluster might be one of the best places in the galaxy for gravitational wave production, with stellar remnants constantly interacting and occasionally colliding. The nuclear star cluster also acts like a natural particle accelerator, using gravitational slingshot effects to launch stars at incredible velocities. Some stars get ejected from the cluster at speeds exceeding 1,000 miles per second, fast enough to escape the galaxy entirely. These hypervelocity stars have been detected racing through the Milky Way's outer regions, stellar refugees from the galactic center's gravitational violence, carrying with them the memory of their chaotic birthplace. Sagittarius A star, the central monster. At the cluster's heart, at the absolute center of our galaxy, lurks a monster, Sagittarius A star. The supermassive black hole at the Milky Way's heart contains the mass of 4.3 million suns crushed into a space smaller than Mercury's orbit. This cosmic giant sits perfectly still at the galaxy's gravitational center, while 400 billion stars orbit around it like moths circling a flame. It's the anchor point that holds our entire galaxy together. For decades, astronomers suspected this monster existed, but they couldn't prove it. The galactic center is hidden behind vast clouds of dust that block visible light, making direct observation impossible. You can point the most powerful optical telescope at the galactic center, and you won't see anything but darkness. But in the 1990s, astronomers began tracking individual stars near the galactic center, using infrared telescopes that could peer through the dust. What they discovered changed our understanding of black holes forever. The stars closest to Sagittarius A star follow elliptical orbits so extreme they stretch the laws of physics. One star, designated S2, completes an orbit around the black hole every 16 years. At its closest approach, it races past the black hole at over 18 million miles per hour, traveling at nearly 3% of the speed of light. The gravitational forces at this distance are so intense they cause measurable effects predicted by Einstein's theory of general relativity. Another star, S29, has an even more extreme orbit. It passes within just 90 astronomical units of the black hole, 90 times the distance from Earth to the Sun. That might sound like a lot, but on cosmic scales, it's incredibly close. The star experiences gravitational forces that are truly mind-bending. By tracking these stars over decades, astronomers were able to measure the mass of Sagittarius A star with incredible precision. The orbital mechanics don't lie. Something with 4.3 million times the Sun's mass sits at the exact center of their orbits, and it's completely invisible. The only thing it could be is a supermassive black hole. But Sagittarius A star isn't content to sit quietly. Though it appears relatively calm most of the time, especially compared to the supermassive black holes in other galaxies, it occasionally flares with activity when gas or debris falls too close. These feeding events can increase the black hole's brightness by factors of hundreds within just minutes, as matter spirals inward and heats to billions of degrees before disappearing forever across the event horizon. The energy released during these flares can outshine all the stars in the nuclear star cluster combined. The black hole becomes, for a brief time, the brightest object in the inner galaxy, visible across the electromagnetic spectrum from radio waves to X-rays. Then, just as quickly, it quiets down again, returning to its baseline level of activity. The black hole's event horizon, the boundary beyond which nothing can escape, has a diameter of about 15 million miles. That might sound large, but it's actually tiny compared to the black hole's sphere of influence, which extends for several light-years in all directions. Within this region, the black hole's gravity dominates everything, controlling the motion of stars, gas clouds, and even light itself. Perhaps the most remarkable discovery about Sagittarius A star came in 2022, when astronomers captured the first direct image of the black hole's shadow. Using the Event Horizon Telescope, a planet-sized network of radio telescopes working together, they photographed the dark silhouette of the event horizon surrounded by a glowing ring of superheated gas. The image confirmed decades of theoretical predictions about how black holes should appear, matching Einstein's equations with stunning accuracy. The magnetic field around Sagittarius A star is millions of times stronger than Earth's magnetic field. This intense magnetism accelerates particles to nearly the speed of light and launches them in narrow jets extending thousands of light-years above and below the galactic plane. These jets carry energy and matter far from the black hole, influencing star formation and gas dynamics throughout the galaxy. Every star in our galaxy, including our Sun, is ultimately orbiting this central monster. Though we're 26,000 light-years away, Sagittarius A star's gravity reaches across the galaxy to guide our motion through space. We're all bound to this object, all participating in the same cosmic dance around the galaxy's gravitational center. The event horizon, edge of forever. The black hole's event horizon represents the ultimate frontier, the place where the normal rules of physics surrender to something far stranger. Cross this invisible line, and you've entered a region of space from which nothing, not matter, not light, not information itself, can ever return. It's the ultimate point of no return, a one-way membrane between our universe and whatever lies beyond. The event horizon isn't a physical surface you could touch or stand on. It's not made of anything. It's a mathematical boundary defined by gravity so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, according to Einstein's special relativity, nothing can escape once it crosses this line. The horizon appears as a perfect sphere surrounding the black hole, with that diameter of roughly 15 million miles we mentioned earlier. But here's where things get really weird, where the universe starts to behave in ways that challenge our everyday intuition. If you somehow approach the event horizon, what you experience would depend entirely on your point of view. To an outside observer watching your journey, you'd appear to slow down as you approached the horizon. Your image would redshift to longer and longer wavelengths as the light from your body struggles to escape the intense gravity. Eventually, you would fade from view, seemingly frozen at the horizon's edge forever. From your perspective, though, your experience would be completely different. You would pass through the event horizon normally, with no special sensation marking the moment you crossed the point of no return. You might not even realize you'd crossed it until you tried to turn around and discovered that every direction now points toward the black hole's center. The horizon would be invisible to you, just empty space that happens to have a special property. The space near the event horizon warps in ways that defy everyday understanding. Tidal forces here are extreme. They would stretch any object that got too close, pulling it apart at the molecular and eventually atomic level, in a process astronomers have colorfully named spaghettification. Your feet would experience significantly stronger gravity than your head if you fell in feet first. This difference would stretch you into a long, thin shape before tearing you apart completely. Time itself behaves strangely near the event horizon. The intense gravitational field causes time to run slower compared to regions farther from the black hole, an effect called gravitational time dilation. A clock at the horizon would tick at a different rate than one in normal space. This means the black hole exists in a different temporal reference frame than the rest of the galaxy. Events that take seconds near the horizon might correspond to minutes, hours, or even years of time passing in the outside universe. The horizon also marks the boundary where space-time curvature becomes effectively infinite from the perspective of the outside universe. At the center of the black hole lies what physicists call a singularity, a point where density becomes infinite and the laws of physics as we understand them break down completely. All the mass of the black hole is compressed into this single point, or possibly into some quantum structure we don't yet understand. The event horizon shields the rest of the universe from direct contact with this cosmic impossibility. Recent theories suggest that black hole event horizons might not be as absolute as once thought. Quantum effects near the horizon could allow some information to escape through a process called Hawking radiation, named after physicist Stephen Hawking, who predicted it. But these effects are so tiny, so impossibly small, that they're completely undetectable for supermassive black holes like Sagittarius A star. They only become significant for much smaller black holes. And even then, the process would take longer than the current age of the universe. Beyond the event horizon lies territory that challenges the very foundations of our understanding of reality. It's a place where time and space exchange roles, where all paths lead inexorably inward to the singularity. It's the ultimate unknown, and unless we develop some completely new physics, it will remain forever beyond our ability to observe directly. Relativistic jets. Escape from the inescapable. From the supermassive black hole at our galaxy's heart, two invisible streams of energy pierce through space at 99% the speed of light. These are relativistic jets, and they extend for thousands of light-years above and below the galactic plane, carrying matter and energy far from the black hole's grip in one of the most spectacular displays of cosmic power in the universe. What makes them even more remarkable is that they originate from something that supposedly allows nothing to escape. But that's the key detail. The jets don't actually come from inside the black hole's event horizon. Instead, they're launched from the swirling disk of superheated gas and plasma spiraling into the black hole, just outside the point of no return. As material falls inward toward the event horizon, it gets compressed and heated to billions of degrees, creating conditions more extreme than the core of any star. The gas doesn't fall straight in, though. It spirals around the black hole in what's called an accretion disk, and this rotation is crucial to jet formation. Magnetic fields threading through this accretion disk get twisted and amplified by the rotation until they become powerful enough to launch streams of particles at relativistic speeds. Think of the magnetic field lines like rubber bands being twisted tighter and tighter. Eventually, the stored energy releases explosively, accelerating charged particles along narrow channels that extend far from the black hole. These jets are incredibly narrow and incredibly focused, maintaining their coherence across thousands of light years with a precision that would be impossible through any human technology. The jets from Sagittarius A star are relatively weak compared to those from more active supermassive black holes in other galaxies. Some galactic jets are so powerful they can be detected from billions of light years away, outshining all the stars in their host galaxies combined. Our galaxy's central black hole is currently in a quiet phase, producing jets that are barely detectable even with our most sensitive instruments. But even these weak jets carry enormous amounts of energy. The particles racing along them have been accelerated to energies millions of times higher than anything achievable in human-built particle accelerators like the Large Hadron Collider. When these high-energy particles interact with magnetic fields or matter along their path, they produce gamma rays, the most energetic form of electromagnetic radiation in the universe. These gamma rays carry so much energy that a single photon can have more energy than visible light photons by factors of millions or billions. The jets also serve as cosmic particle accelerators, creating some of the highest energy cosmic rays that bombard Earth's atmosphere. These particles travel so fast that time dilation effects become significant. A particle in one of these jets experiences time passing much more slowly than we do, meaning its journey across the galaxy takes only minutes or hours from its own perspective, even though thousands of years pass in our reference frame. Recent observations have revealed that the jets from Sagittarius A star change direction over time. The black hole's rotation axis doesn't always point in the same direction, causing the jets to wobble like water from a spinning sprinkler. This precession occurs over timescales of thousands of years, slowly sweeping the jets across different regions of the galaxy. The jets also interact with the surrounding interstellar medium, creating shockwaves and heating gas clouds they encounter along their path. This process helps regulate star formation in the galaxy by injecting energy into molecular clouds that might otherwise collapse to form new stars. In this way, the supermassive black hole influences conditions throughout the galaxy, not just in its immediate vicinity. Time dilation and warped spacetime. Near the supermassive black hole at our galaxy's center, time itself becomes a variable. The intense gravitational field warps the fabric of space-time so severely that clocks run slower, distances stretch, and the fundamental nature of reality bends in ways that would seem impossible anywhere else in the universe. Welcome to the realm where Einstein's wildest theories become everyday physics. This time-warping effect, called gravitational time dilation, means that time passes differently depending on how close you are to the black hole. A clock placed just outside the event horizon would tick significantly slower than an identical clock in normal space. From our perspective on Earth, 26,000 light-years away, that clock would appear almost frozen, its hands barely moving as gravity stretches each second into an eternity. The effect isn't subtle at extreme distances. Near the event horizon of Sagittarius A star, time dilation becomes infinite from an outside observer's perspective. This means that anything falling toward the black hole would appear to slow down dramatically as it approached the horizon, its image redshifting and fading until it became invisible, seemingly frozen at the edge of forever. But the time warping extends far beyond the event horizon itself. Stars orbiting close to the black hole experience measurable time dilation effects. The star S2, which we encountered earlier racing around the black hole every 16 years, actually ages slightly slower than it would if it orbited farther away. Over millions of years, this difference could add up to thousands of years of extrastellar lifetime. Astronomers have actually measured these time dilation effects by observing the light from S2. As the star approaches the black hole at its closest point, the light coming from it shows a gravitational redshift, a shift toward longer wavelengths caused by the intense gravity. This redshift matches the predictions of general relativity perfectly, providing yet another confirmation of Einstein's theory. The warping of time is intimately connected to the warping of space. Near the black hole, space itself becomes curved, like a bowling ball creating a depression in a stretched rubber sheet. This curvature affects not just the passage of time, but also the paths that light and matter must follow. Straight lines in normal space become curved trajectories in the black hole's vicinity. One of the most mind-bending consequences of this space-time warping is the existence of what physicists call photon spheres. At a distance of about 1.5 times the event horizon radius, light can orbit the black hole in circular paths. If you were somehow positioned at this distance, you could theoretically see the back of your own head as light from you travels around the black hole and returns to your eyes. The time dilation effects near Sagittarius A star also influence the light we receive from objects in that region. Radio signals from gas clouds spiraling into the black hole arrive at Earth with their frequency shifted by the gravitational field. This gravitational redshift provides astronomers with a direct measurement of the black hole's mass and the strength of its gravitational field. The dark matter halo and galactic context. As we pull back from this region where time itself bends and breaks, as we zoom out to see the galaxy as a whole, we begin to understand that our entire galaxy is embedded in an even larger and more mysterious structure. Surrounding the Milky Way's visible stars and gas clouds is a massive spherical halo made of dark matter, a substance that outweighs everything we can see by a factor of about 10 to 1. This dark halo extends far beyond the galaxy's spiral arms, creating an invisible architecture that holds our cosmic home together and determines how it moves through the universe. Dark matter doesn't emit, absorb, or reflect light of any kind. It's completely invisible to every form of electromagnetic radiation, from radio waves to gamma rays. The only way we know it exists is through its gravitational effects on the visible matter around it. Stars in the outer regions of galaxies orbit faster than they should based on the visible mass alone. When astronomers calculated how fast stars should be moving based on the mass they could see, they found a huge discrepancy. The stars were moving too fast. They should be flying off into space, unbound by the galaxy's gravity. But they're not. Something with tremendous gravitational pull must be holding them in their orbits. That something is dark matter. The Milky Way's dark halo is enormous, extending out to distances of at least 600,000 light-years from the galactic center. That's 3 times larger than the visible galaxy, and large enough to encompass several of our satellite galaxies. If you could somehow see dark matter, our galaxy would look like a small, bright disk floating at the center of a much larger, diffuse sphere. This invisible halo contains roughly 1 trillion solar masses worth of dark matter, making it by far the most massive component of our galactic system. All the stars, gas, dust, planets, everything we can see and touch and measure directly in the Milky Way combined represents only about 15 to 20% of the total mass. We're essentially living inside a dark matter structure with some normal matter sprinkled on top, like seasoning on a vast cosmic meal. The nature of dark matter remains one of the biggest unsolved mysteries in science. Leading candidates include exotic particles that interact only through gravity and possibly the weak nuclear force, making them nearly impossible to detect directly. These hypothetical particles have names like WIMPs, weakly interacting massive particles, and axions. Laboratory experiments around the world are searching for signs of these particles, but so far, dark matter continues to live up to its name, remaining frustratingly elusive. Satellite galaxies and cosmic neighbors. Our galaxy is not alone. Orbiting the Milky Way like cosmic moons around a planet are dozens of smaller galaxies, gravitational captives locked in an eternal dance with our galactic giant. These satellite galaxies range from tiny collections of a few million stars to substantial stellar cities containing billions of suns. Together, they form a complex gravitational ecosystem that has been evolving for billions of years. The most famous of our satellite galaxies are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light. The Large Magellanic Cloud contains about 30 billion stars, making it roughly 1/10 the mass of the Milky Way. Its smaller companion harbors around 3 billion stars, still massive enough to support active star formation and its own internal structure. But these prominent satellites are just the beginning. Astronomers have discovered over 50 smaller satellite galaxies orbiting the Milky Way, with names like Draco, Ursa Minor, Sculptor, and Sagittarius. Most of these are dwarf galaxies containing anywhere from a few thousand to a few billion stars. They're spread across the sky in all directions, some as close as 75,000 light-years, and others as distant as several 100,000 light-years from our galactic center. The relationship between the Milky Way and its satellites is complex and often violent. Our galaxy's superior gravitational pull strips stars and gas from smaller companions that venture too close. The Sagittarius dwarf elliptical galaxy is currently being torn apart by this process, leaving long streams of stars scattered across our sky like cosmic contrails. Over hundreds of millions of years, these stellar streams will be completely absorbed into the Milky Way's outer regions, the satellite galaxy consumed by our larger mass. Some satellite galaxies show signs of multiple episodes of star formation, triggered by close encounters with our galaxy. As they swing through their elliptical orbits, gravitational forces compress their internal gas clouds, sparking bursts of new stellar birth. These interactions create irregular patterns of stellar ages within the satellites, like geological layers recording their orbital history. Trailing behind the Magellanic Clouds like a cosmic contrail stretches one of the largest structures associated with our galaxy. The Magellanic Stream is a river of hydrogen gas extending over 600,000 light-years across our sky, longer than the diameter of our entire galactic disk. This enormous streamer of material tells the story of a slow-motion collision that has been unfolding for billions of years. The stream formed through gravitational theft on a galactic scale. As the large and small Magellanic Clouds orbit our galaxy, the Milky Way's superior gravitational pull strips away their outer layers of gas. This stolen material doesn't fall directly into our galaxy. Instead, it gets stretched into long tidal tails that trace the orbital path of the Magellanic Clouds through space. The stream contains enough material to build 2 billion stars like our Sun. That's more gas than exists in many entire galaxies, all stretched across hundreds of thousands of light-years of space. As this material eventually falls into the Milky Way over the next few billion years, it will trigger new episodes of star formation throughout our galactic disk, providing fresh fuel for stellar nurseries. The future collision with Andromeda. In about 4.5 billion years, our night sky will transform into something unrecognizable. The Andromeda Galaxy, currently racing toward us at 250,000 miles per hour, will collide with the Milky Way in the most spectacular cosmic event our galaxy will ever experience. This collision will reshape both galaxies, flinging stars into new orbits and potentially triggering the largest burst of star formation in either galaxy's history. Don't let the word collision fool you, though. When galaxies collide, individual stars almost never actually hit each other. The distances between stars are so vast that most would pass through the chaos unaffected, like two swarms of bees passing through each other. Instead, it's a collision of gravitational fields, gas clouds, and dark matter halos. The overall structure of both galaxies will be completely transformed, but the process will unfold over hundreds of millions of years. Andromeda is the largest galaxy in our local group of galaxies, containing roughly 1 trillion stars compared to the Milky Way's 400 billion. It's also approaching us nearly head-on, which will make the collision even more dramatic than if the galaxies were to experience a glancing blow. Computer simulation suggests the initial encounter will send streams of stars flying out into intergalactic space, creating spectacular tidal tails hundreds of thousands of light-years long. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other, creating one of the most energetic events possible in the universe. As these monsters orbit closer and closer together, they'll generate gravitational waves that will ripple through space-time itself. The final merger of the black holes will release more energy in gravitational waves than all the stars in both galaxies combined produce in light. Our solar system will likely survive this cosmic reshuffling, though our location within the new merged galaxy will probably change dramatically. The Sun and its planets might get flung to the outer regions of the merged galaxy, or we could end up closer to the new galactic center. The good news is that by the time this collision occurs, the Sun will be entering its red giant phase anyway, so Earth's habitability will already be compromised by our star's evolution. Astronomers have already given this future merged galaxy a name: Milkomeda or Milkdromeda. It will likely be an elliptical galaxy rather than a spiral, as the collision will disrupt the organized rotation patterns that maintain spiral structure. The new galaxy will be larger and more massive than either of its parents, containing the combined stellar populations of both the Milky Way and Andromeda. Our place in the cosmic web. After traveling from our local solar neighborhood to the very edge of the Milky Way and beyond, it's time to zoom out one final time and see where we truly live in the cosmic hierarchy. Our complete cosmic address reads like a map of nested structures, each one larger and more magnificent than the last. We start with Earth, orbiting the Sun in a solar system located in the local bubble within the Orion arm of the Milky Way galaxy. But that's just the beginning of our address. Our galaxy belongs to the local group, a collection of over 80 galaxies dominated by the Milky Way, Andromeda, and Triangulum. This entire group spans about 10 million light-years and contains roughly 3 trillion stars. The local group, in turn, sits on the outskirts of the Virgo cluster, a massive collection of over 2,000 galaxies centered about 54 million light-years away. The Virgo cluster contains some of the largest galaxies known, including the giant elliptical M87 with its 6.5 billion solar mass black hole. Our local group is slowly falling toward this cluster, accelerated by its immense gravitational pull. But even the Virgo cluster is just a small part of something much larger. It sits near the center of the Virgo supercluster, also called the local supercluster, a vast sheet of galaxies and galaxy clusters stretching across 110 million light-years. This structure contains roughly 100,000 galaxies and represents one of the largest coherent structures in the nearby universe. Recent discoveries have revealed that our supercluster is itself part of an even larger structure called Laniakea, Hawaiian for immeasurable heaven. This supercluster of superclusters spans 500 million light-years and contains the mass of 100 quadrillion suns. The gravitational center of Laniakea, called the Great Attractor, is pulling our entire local group toward it at over 1 million miles per hour. But the cosmic hierarchy doesn't stop there. Laniakea connects to other superclusters through vast filaments of dark matter and galaxies, creating a cosmic web that spans the observable universe. Between these filaments lie enormous voids, cosmic deserts containing almost no galaxies at all. Some of these voids are so large that light takes hundreds of millions of years to cross them. Understanding our place in this cosmic hierarchy puts everything in perspective. The journey we've taken from Earth to the galactic center and beyond represents just one tiny thread in the vast cosmic web. Yet within that web, on a small rocky planet orbiting an ordinary star, something extraordinary has happened. Matter has organized itself into forms complex enough to contemplate its own existence and map the very structures that contain it. We are the universe becoming aware of itself, one galaxy at a time. We began this journey 26,000 light-years from home, racing through space at 500,000 miles per hour. We've witnessed stellar nurseries giving birth to giants, explored the hidden architecture of spiral arms, and stared into the face of a monster black hole that anchors our entire galaxy. From the quiet bubble of space around our solar system to the cosmic web that connects superclusters across hundreds of millions of light-years, we've traced the path from the familiar to the almost unimaginable. The Milky Way isn't just our cosmic home. It's a dynamic, evolving system where matter and energy dance on scales that stretch human comprehension to its limits. Every element in your body was forged in the nuclear furnaces of stars that lived and died long before our solar system existed. The carbon in your cells, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it came from stellar furnaces that burned billions of years ago. You are literally made of galactic recycled material, assembled from stellar ash that has journeyed across space and time to become part of something capable of understanding its own origins. But perhaps the most remarkable discovery from our galactic odyssey is how much we still don't know. Dark matter outweighs everything we can see by 10 to 1, yet its nature remains completely mysterious. We don't know what particles it's made of. We don't know exactly how it behaves beyond its gravitational effects. And despite decades of searching, we haven't detected a single dark matter particle directly. The supermassive black hole at our galaxy's heart follows the laws of physics into realms where space and time themselves break down. What happens at the singularity? What lies beyond the event horizon? These questions push against the boundaries of our current physics, hinting at deeper theories we haven't discovered yet. The cosmic web that connects galaxy clusters across the universe appears to be accelerating apart due to an even more mysterious force called dark energy. This makes up about 70% of the energy content of the universe, yet we have no idea what it actually is. We can measure its effects. We can track how it's causing the universe's expansion to accelerate, but we don't understand its fundamental nature. We live in an age of cosmic discovery unprecedented in human history. Every year brings new revelations about our galactic home. We've detected gravitational waves rippling through spacetime from colliding black holes billions of light-years away. We've captured direct images of black hole event horizons, confirming predictions made a century ago. The James Webb Space Telescope is revealing galaxies from when the universe was young, just a few 100 million years after the Big Bang. Ground-based observatories are mapping the motion of individual stars around our galaxy's central black hole with incredible precision, testing Einstein's theory in the most extreme gravitational environment we can observe. Yet for all our cosmic knowledge, we remain the only known observers in this vast galactic theater. In a galaxy containing 400 billion stars, on a planet perfectly positioned in the galactic habitable zone, matter has organized itself into forms complex enough to contemplate the very structures that contain it. Whether that makes us incredibly special or cosmically typical remains one of the greatest unanswered questions. The next time you look up at the night sky, remember that you're seeing just the nearest edge of a galactic city containing more stars than there are grains of sand on all of Earth's beaches. You're orbiting one of those stars at 500,000 miles per hour, carried along by gravitational forces that reach across the galaxy to touch our motion, the faint band of light stretching across the dark sky. That's our view from inside the galactic disk, looking edge-on at billions of stars too distant to resolve individually. Our journey to the center of the Milky Way reveals that we don't just live in the universe. We are the universe, organized into temporary patterns capable of mapping our own cosmic context. In understanding our galaxy, in tracing this path from Earth to the supermassive black hole at the center and back out to the cosmic web beyond, we understand ourselves. We see where we came from, we glimpse where we're going, and we recognize our place in the grandest story ever told, the story of cosmic evolution, of matter becoming conscious, of the universe awakening to contemplate itself. If this journey through our galaxy has changed how you see the cosmos, if it sparked your curiosity about the universe we inhabit, hit that like button and subscribe to Behind the Space. We're exploring the universe one incredible discovery at a time, and there are so many more journeys to take together. From black holes to distant galaxies, from the birth of stars to the death of the universe, we're here to take you along for the ride. Thanks for joining me on this journey to the center of the Milky Way. Until next time, keep looking up